So welcome to tutorial 4th of a DC machine. In this tutorial we are going to solve problem on losses and efficiency. So problem number 1 is on shunt generator which is delivering 195 ampere at a terminal potential difference of 250 volt. So 195 ampere is the terminal current and 250 volt is the terminal voltage. The armature resistance and shunt field resistances are given as 0.02 ohms and 50 ohm respectively. The iron and friction losses equal to 950 watt. So iron plus friction losses is given to be 950 watt. You have to calculate the EMF generated, e.g. you have to calculate the copper losses. You have to calculate the output of the prime mover and commercial, mechanical and electrical efficiency. So this is problem number 1 and the generator is basically a shunt generator. So the data that are given to us is basically the line current IL, the line voltage VL and the resistances of the armature RA and RSH and the total losses comprising of iron and friction losses. So let us see the solution then. So first you calculate what is the shunt current. So basically this is a shunt generator. So the total voltage that appear at the terminal divided by the shunt resistance will give you the shunt current. So shunt current will comes to be 5 ampere. Now the current, armature current will divide into two different parts, that is the armature current will divide into the shunt current plus the line current. Here the line current is given to be 195 ampere and 5 ampere is the shunt current, so the armature current is 200 ampere. Now determine the armature voltage drop. So you have determined the armature current and armature resistance is given to you. So just multiply the armature current and armature resistance, which is 200 multiplied with 0.02. You will get 4 volt as the armature voltage drop. So the generated EMF will be equal to the terminal voltage plus the drop which is there at the armature. So armature drop is 4 volt and the generated EMF is terminal voltage is 250. So you will get 254 volt as the generated EMF. Now determine the copper loss. So armature copper loss is basically Ia square Ra. So whenever the copper loss we have to determine by I square R. So here we are determining for the armature. So we are providing the current for the armature and the resistance of the armature. So armature current here we have obtained as 200 ampere. So 200 square multiplied with the resistance of the armature, that is 0.02, you will be getting a loss of 800 watt. Now determine the shunt copper loss. So you have determined the voltage that is across the shunt field winding, which is the terminal voltage multiplied with the shunt current that you have determined, that is 5 ampere. So terminal voltage into the shunt current, that is 1250 watt, that is the shunt copper loss. Now the total copper loss is basically the adding up of the shunt copper loss plus the armature copper loss. So shunt copper loss is 1250 and armature copper loss is 800. You add up, so you'll get the total copper loss as 2050 watt. Stray losses is being given to you as 950 watt, that is the combination of the friction losses and the iron losses. So total losses that you have is basically the sum of copper loss plus the stray loss. So copper loss plus stray loss will give you the total loss, that is equal to 3000 watt. Now determine the output power. So output power you can determine as the product of the voltage and the current. So the terminal voltage multiplied with the terminal current or the load current will give you the output power, that is 48.75 watt. So this is the output power. Now input power is equal to output power plus the losses that you have computed. So losses you have computed at 3000 watt. So just add up with the output power. So you will get 51750 watt as the input power. Now the input power is basically the output of the prime mover. So this is a generator. So the input power is output of the prime mover, which is same as 51750, and this is the generator input. So generator input is 51750 watt. So the stray losses is given to be 950 watt at the beginning. So you can easily determine the power produced in the armature. So what is the power produced in the armature? This is the electrical input power minus the stray losses, whatever is given to you. So this is the stray losses that you take out from the power. You will be getting 5800 watt. Now we have to determine the mechanical efficiency, electrical efficiency, and the commercial efficiency. So mechanical efficiency, whatever you are getting after subtracting the stray losses, the power 5800, you just divide it with the power of the input. Then you will get 98.2% as the mechanical efficiency. The electrical efficiency will be computed by computing the copper losses. So copper losses is given to be 2050 watt. So electrical efficiency you can compute as output power by input power, that is output power plus losses. So this here you have the copper loss. So copper loss into 100, you will get 95.9%. Then the commercial efficiency that you are having is basically the output power divided by the total input power that you have into 100. You will get 94.2% as the commercial efficiency. So after seeing problem number 1, let us see the problem number 2. So problem number 2, you have a shunt generator. Its full load current is given to be 196 ampere at 220 volt. So this is again the line current and this is the line voltage. The stray losses are 720 watt and the shunt filled copper resistance is given to be 55 ohms. So you have been given the RSH value as 55 ohms. If it has a full load efficiency of 88%, find the armature resistance. So what is the armature resistance of the DC shunt generator when the efficiency is 88%? Also find the load current corresponding to maximum efficiency. So what is the load current when your efficiency is at maximum condition? Now note down here that the word efficiency has been used without using the term whether it is a mechanical efficiency, electrical efficiency or overall efficiency. When under the such condition, you will be taking this efficiency as the overall efficiency or the electrical efficiency. Okay, so let us solve this problem number 2, where you have to find out the armature resistance and you have to find out the load current when your efficiency is maximum. So let us see the solution. So what is the output power? So output power is basically the product of the line voltage multiplied with the line current. So you will be getting 43120 watt. Then the overall efficiency is given to be 88%. So the total losses that, so here we have not computed one thing, that is the output power is 43120 divided by the efficiency, because the efficiency is basically the output power by input power. So if you compute the output power is given to you and efficiency is given to you, so input you can determine. So input if you want to determine, then it is equal to 43120 divided by 88%. So if you do that, you will be getting 49 kilowatt as the input power. This is the input power you will be getting. So input power minus the output power, you will be getting the losses. So total losses you will be getting as 5880 watt. So here the one calculation is missing, that is what is the input power. So input power you compute from the output power by efficiency. So now we have computed the input power and what is the total losses in the machine. The shunt field current you can compute similarly to the previous case, that what is the load voltage and the load current. You will be getting 4 ampere as the shunt field current. Then armature current you compute, since it is a shunt machine, so armature current will be equal to the load current plus the current which is flowing in the shunt or the field winding. Then you are getting 200 ampere. So shunt copper loss is basically the loss you are computing. So multiplied the voltage with the current, that will give you the shunt copper loss. So you are getting 4 ampere as the shunt current ISH, and the resistance of the shunt is being given to you as the 220 ohms. So the total power you are getting, sorry, the voltage is 220 volt, so you are getting a power of 880 watt. Here the stray losses is mentioned to be 720 watt, which is given in the question. Sorry, I just told that it is not mentioned, but in the problem it is mentioned as 720 watt. So the constant losses whatever is there in the machine, which is the basically the sum of the 880 watt, that is the iron loss, plus the stray losses. You know that there are two type of losses, one is constant loss, another is variable loss. Variable loss is basically whatever the loss that is being taken place in the copper winding. Now here you have the shunt, and you know the shunt machine is a constant flux machine. So whatever the loss that will be occurring in the shunt field winding, it will be considered as the constant loss, because the entire terminal voltage is applied across the field winding. So 880 watt plus the stray losses will be considered as the constant losses of the machine, that is 1600 watt. Now armature copper loss you compute. So here you have computed the constant losses, that is 1600 watt, and you know the total losses is 5880 watt. So copper losses, entire copper losses will be 5880 minus 1600. So you'll get 4280 watt as the armature copper loss. Now you know the condition that the efficiency will be maximum under the condition that the total constant losses is equal to total variable losses, right? So here 4280, which is the armature copper loss, we take at 4280, which is equal to Ia square Ra. Now the first condition was to determine what is the armature resistance. So armature resistance will be determined from the losses that is being taken place in the armature. So Ia square Ra is equal to 4280. Now Ia you have already computed. So put the value of Ia, and 4280 is given to you have computed as armature copper loss. So determine the resistance of the armature. So resistance of the armature you will get 0.107 ohms. So this was the first case. Now your efficiency maximum condition is coming. So efficiency maximum is when your constant losses is equal to your variable losses, right? So in this case you will be taking for time to find out what is the current, load current corresponding to the maximum efficiency. So armature resistance you have computed here 0.107, and constant losses you have computed as 1600 watt. So the load current IL will be under root of the total constant losses divided by the armature resistance. So you will be getting 122.34 ampere as the load current corresponding to the maximum efficiency. So this is the problem number 2. So problem number 3, let us see. So in the problem number 3, you are dealing with long shunt generator. So you know what is a long shunt generator? It is running at 1000 rpm. So it is a compound generator which is running at 1000 rpm. So this is the speed which is being given to you, and it is supplying 22 kilowatt at a terminal voltage of 220 volt. So this power 22 kilowatt which is supplying is basically the load power, and the terminal voltage is given to you as 220 volt. Now all the resistances of the armature, shunt field winding and series field winding are given to you respectively as 0.05, 110 and 0.06 ohm respectively. Now since it is a shunt generator, a long shunt generator which is a compound generator, it will be combination of shunt field as well as series field with a definite connection. Now the overall efficiency of the load is given to be 88%. You have to compute the copper loss, you have to compute the iron and the friction losses, and the torque exerted by the prime mover. So what is the torque that is exerted by the prime mover? So three things you have to calculate for problem number 3. So let us see the solution then. So first draw the circuit diagram of a long shunt compound generator. So this is your long shunt compound generator. In the long shunt compound generator, your shunt field winding will be coming in parallel with the entire armature as well as the series field winding. So this is your series field winding, and this is your load whatever you have at the terminal. So the information of the load power is given, that is 22 kilowatt, and the voltage is given 220 volt. So first you determine the shunt current. So shunt current will be equal to the total voltage whatever is applied in the shunt field winding divided by the shunt resistance. So shunt field voltage will be equal to the load voltage because it is coming entirely in parallel with the load. So 220 volt is the load voltage and 110 is the resistance of the shunt. So you will get 2 ampere as the shunt current. Next, calculate the load current then. So load current can be calculated from the formula of the load power divided by the load voltage. Okay, so load power you have been given 22 kilowatt, so it's 22,000 watt divided by the load voltage, that is 220 volt. So you will get 100 ampere as the current which is flowing in the load. So 100 ampere is the current which is flowing in the load. Now the armature current is divided into the shunt current and the load current. So apply the KCL equation. So once you apply the KCL equation, you will be adding the shunt current and the load current. You will be getting the armature current as 102 ampere. So what is the drop that is there in the series field winding? So this is the series field winding. What is the drop? So the drop is basically the resistance of the series field winding multiplied by the current which is flowing in the series field winding. So this is the total drop in the series winding. So series winding is having a drop of 6.12 volt. Now what is the drop across the armature? What is the power across the armature? So armature is having a resistance of 0.05 and the current that is flowing in the armature you have computed as 102. So 102 square into the resistance of the armature, you are getting 520.2 watt. That is the copper loss in the armature. Next, you calculate what is the series field loss. So series field loss can be computed from the knowledge of the current which is flowing in the series field winding. So series current will be equal to the armature current. So 102 square multiplied with the resistance of the series, which is equal to 624.3 watt. And shunt field loss, so this is your shunt field. What is the loss here you have? So here you are getting a 110 as the resistance of the shunt field winding multiplied with the what is the current which is flowing, ISH square. So current is flowing as 2 ampere. So 2 ampere square is 4 multiplied with 110. You are getting 440 watt as the loss in the shunt field loss. So the total copper loss you can calculate now. So the total copper loss is basically 520.2, which is due to the armature, and 624.3 which is due to the series field winding, and 440 watt due to the RSH. So this is the total copper loss in the three resistances which are there in the armature, series and shunt. So you are getting 1584.5 watt. So you are computing the total copper loss as the sum of the armature, series and the shunt losses. Then the output power, that is across the load, is already given to be 22 kilowatt. So it is 22,000 watt. Then input you can compute as the output power divided by the efficiency of the machine. So efficiency is given to be at 88%. So please put 0.88, converting the percentage to the fraction. So you are getting 25,000 watt as the input power. So total losses in the machine now will be the input power, that is 25,000, minus the output power, that is 22,000. So you'll be getting 3,000 watt as the total losses in the machine. So it has been asked in the question that what is the iron and the friction losses. So iron and the friction losses you can compute from the knowledge of the total losses, that is 3000 watt, and the knowledge of the total copper loss. So total copper loss is given to be 1584.5, that is the copper loss, and this is the total loss. So you subtract the total loss from the copper loss, then you will get what is the iron and friction losses. So it is 1415.5 watt. Now next you have been asked what is the torque. So you can use the formula of the torque. So power is equal to torque into omega, where omega you can write as 2 pi n by 60. So you can substitute omega here. So this is the power, and 2 pi n by 60 is your omega, that is the speed in radian per second, whereas n is the speed in RPM. So you substitute pi, 3.14, and this is the power 25,000, 25 kilowatt is the power of the output. So the torque can be obtained from the knowledge of this equation. So you'll get 238.74 and the unit is Newton meter. So in this way we have solved problem of determining the losses as well as the torque. So problem number 4th. So problem number 4th is, you have been given a 4-pole DC generator which is delivering 20 ampere. So here it is the load current because you are dealing with the generator to a load of 10 ohms. So the load resistance is given to be 10 ohms. If the armature resistance is 0.5 ohms and the shunt field resistance is 50 ohms, calculate the induced EMF and the efficiency of the machine. Allow a drop of 1 volt per brush. So you know that 2 brushes will be there and 1 volt is there drop which is across the per brush. So total drop will be 2 volt across the 2 brushes, and the machine information is given as 4-pole DC generator. Okay, so the number of poles is given, the load current is given, load resistance is given, armature resistance and shunt field resistances are given. You have to determine the induced EMF and the efficiency of the machine. So let us see the solution. Now first you draw the diagram of the DC machine. So considering it is a shunt machine, whenever no information is given on the machine, every time we just consider it to be a shunt machine. Okay, so in the shunt machine you first determine what is the terminal voltage. So at the terminal the voltage will be the multiplication of the terminal current multiplied with the load resistance. So load resistance is given to be 10 ohms and the current which is delivering is 20 ampere. So if you multiply 20 ampere with 10 ohms, you will be getting the load voltage or the terminal voltage as 200 volt. Then once the knowledge of 200 volt we get it at the terminal, it will be easy to compute the shunt current. So the current that is flowing across the shunt field winding is the total voltage of the load load divided by the resistance of the shunt, so it is equal to 4 ampere. Now you can compute the armature current applying the KCL equation. So armature current is divided into the shunt current and the load current. So the load current is 20 ampere and 4 ampere is the shunt current. So you will get 24 ampere as the current flowing from the armature. Now the drop across the voltage drop across the armature is IARA. So the current you have computed as 24 ampere and the resistance of the armature is 0.5 ohms. So you'll get 12 volt as the drop across the armature. And in addition, there are two brushes in the armature, so that will give you 2 into 1 volt brush drop, that is 2 volt as the total brush drop. So the generated EMF will be equal to the terminal voltage, whatever the terminal voltage you have, plus the drop that is there in the armature plus the drop that is there in the brush. So applying the KVL equation, you will get what is the generated EMF. So generated EMF is the net total voltage at the terminal plus the armature drop plus the brush drop. So you'll get 214 volt as the generated EMF. Now, since iron and friction losses are not given and only electrical efficiency of the machine can be found out. Okay, so you have not been given the information of iron and friction losses, so you can compute the electrical efficiency. So electrical efficiency means what is related to the armature. Okay, so total power generated in the armature first you compute. So power relationship you can compute from the knowledge of the voltage and the current. So here in the armature, the net generated EMF is 214 volt and the 24 ampere is the current which is coming out from the armature. So net power is 5.136 watt, that is the generated from the armature end. And the useful output means what is the power that is obtained in the load, that is the useful output. So it is equal to 200 volt, that is the voltage, multiplied with the current 20 ampere. So you'll get 4 watt as in the load. So in the load you are getting 4 watt. So the electrical efficiency that you are going to compute now from the knowledge of the armature and the load you will be computing. So this is your output and this is your input. So output you are getting 4 kilowatt divided by 5136 watt. So this one is equal to 0.779, that is 77.9%. So in this way you can calculate the efficiency of the machine. So we will solve the problem number 5th. Now in the problem number 5th you have a long shunt compound wound generator. So it is direct information is given, long shunt. So long shunt machine is there. So obviously you will be giving the information of the shunt as well as series field winding. Now it is giving 240 volt at full output of 100 ampere. So this is the meaning that 240 volt is the load voltage and the current 100 ampere is the load current. So load current and load voltage information is given. The resistance of the winding, that is the armature, which is including the brush contact drop, is 0.1 ohms. Series field is 0.02 ohms and interpole field winding is given to be 0.025 ohms. Shunt field, which is including the regulating resistance, is 100 ohms and the iron loss at full load is given to be 1000 watt. The windage and friction losses is given to be 500 watt. Then you have to calculate the full load efficiency of the machine. So what is the full load efficiency of the machine? Machine is long shunt compound generator. So all data are given, the load voltage, load current and different resistances of the armature, series and the shunt. So the brush contact drop and everything are included in the armature and the iron loss information is given and stray losses information is given to you. So let us see the solution. So First, you determine what is the output power. So output power is basically the voltage across the load multiplied by the current in the load. So you'll get 24 kilowatt as the output power. Total armature circuit resistance. So what is the total armature circuit resistance you have? So from the data that is being given to you, you have been given three datas you have been given. Please note down. One is the armature you have been given, which is 0.1 ohms. Interpole field, which is in series with the armature, so it is 0.025. It is given to you, and you have been given as 0.025 and 0.02 and 0.01. So three resistances together will make to be your armature circuit resistances. So this is in accordance with the construction of the DC machine. So the total resistance is coming to be 0.145 ohms. Now it is a long shunt. So obviously you draw the circuit of the long shunt. So you will be having a machine here, and the series field winding will be here, and the entire shunt field winding will be coming in parallel with the entire load, and this is your load. So what is the current that is flowing in the shunt field winding? So current that is flowing in the shunt field winding will be the total voltage which is there in the load divided by the resistance of the shunt. So resistance of the shunt is 100 and the voltage is 240 volt, which is there at the load voltage. So load voltage divided by RSH, you will get the shunt current. So shunt current is 2.4 ampere. Armature current again will be divided into two categories. You apply the KCL equation. One is shunt current plus the load current will give you the armature current. So 100 ampere and 2.4 ampere, that is the shunt current plus the load current, will give you 102.4 ampere as the armature current. What is armature circuit copper loss? So what is the copper loss? So copper loss in the armature. So you have been given the total resistance as 0.145 and the current is 102.4. So Ia square multiplied by the Ra total. So you will get 1521 watt as the total armature circuit copper loss. Shunt field copper loss, you just determine what is the shunt field copper loss. So 2.4 ampere is the current which is flowing in the shunt ISH, and the voltage of the load VL you have to multiply. You will be getting the shunt field copper loss as 576 watt. Iron loss is given to be 1000 watt and friction loss is given to be 500 watt. So this information is already given in the question. So total loss, what is there? So total loss is basically the combination of the iron loss, the total loss is the combination of the copper loss which is taking place in the armature plus the loss that you have in the iron and the friction losses and the shunt field losses. So this is the resistance of the shunt and this is the armature copper loss Ra, and this is combination of iron plus friction. So these together will give you the total losses in the machine. So it is equal to 3.597 watt. I think it is 3597 watt you will be having. So just determine the efficiency of the machine. Efficiency of the machine is what is the output power by the input power. So input power can again be written as output power plus losses. So output power is at the load which is 24,000 watt and the losses you have determined as 3597 watt. So just put it, you'll get an efficiency of 87% for the machine. So this complete the tutorial number 5th.